Alright, in this video, I'll be solving my CIE A-Level Maths 9709 Stats 2 May June 2025 case paper. If you're feeling anxious, overwhelmed, or unsure where to start, then I've created a complete course that streamlines everything with step-by-step videos, interactive quizzes, and an exclusive student community to keep you on track. You can get access to it by clicking the first link in the description. Otherwise, like the video, subscribe, and let's dive right in. Number 1. The numbers of cars passing through toll booths X and Y during a 10-minute period have the independent distributions Poisson with lambda 3.4 and Poisson with lambda 2.7 respectively. Part A. Find the probability that during a randomly chosen 16-minute period, at least 5 cars will pass through toll booth X. Alright, so notice that initially when we are given these numbers, these were defined for a 10-minute period. But in our question, we are dealing with a 16-minute period. So if I'm to define our random variable, we can call it B. Let B be the random variable number of cars passing through toll booth X, passing through booth X per 16-minute period, right? Per 16-minute period. Per 16 minutes rather. So B is going to follow a Poisson distribution. But the lambda now, because we've changed the interval, lambda has to change. We know that for 10 minutes, our lambda is 3.4. What about for 16 minutes? It's going to be 16 over 10 times the 3.4. And this should be, that's 16 over 10 times 3.4. So our lambda becomes 5.44. So B follows a Poisson distribution with lambda 5.44. And we want to find the probability that B is at least, so greater than or equal to 5. All right, we can rewrite this as 1 minus the probability that X is less than 5. So that's going to be 1 minus the probability that X is 4, 3, 2, 1, or 0. Okay, so let's evaluate this. This is 1 minus e to the negative lambda. Lambda is 5.44. And then we've got probability that X is 4. That's 5.44 to the 4 over 4 factorial. Plus X is 3. That's 5.44 to the 3 over 3 factorial. Plus X is 2. That's 5.44 to the 2 over 2 factorial. X is 1 is just 5.44. And X is 0 is just 1. Let's punch this into the calculator. That's 1 minus e to the negative 5.44 times 5.44 to the 4 over 4 factorial plus 5.44 to the 3 over 3 factorial plus 5.44 squared over 2 factorial plus 5.44 plus 1. So we get a final answer of 0.633. Now part B says find the probability that during a randomly chosen 4-minute period, the total number of cars passing through both toll booths is less than 3. Okay, so again notice how our interval has changed here to a 4-minute period. And now we want the total number of cars passing through both the toll booths X and Y. Alright, so let's define our random variable. We'll call it T. That will be the total number of cars passing through both X and Y, passing through both booths per 4-minute period or per 4 minutes. Okay. So T is going to follow a Poisson distribution. All right, and our lambda is going to be, first we need to find the number of cars passing through the toll booth X in a 4-minute period. So we know that for X, in a 10-minute period, we've got 3.4 cars, but we want 4, so it's going to be 4 over 10. Okay, so that's 4 over 10 times 3.4, which is 1.36. So this 1.36 is the number of cars passing through X, cars passing through X, per 4 minutes. We need to do the same for Y. So we know that per 10 minutes for Y, we've got 2.7 cars passing through the booth, but we want again 4 minutes, so it's 4 over 10, which is 4 over 10 times 2.7. That gives us 1.08, 1.08. So this becomes the number of cars passing through Y per 4 minutes. All right, and we want the total, so it means we're going to have to add these two values, 1.36 plus 1.08. So 1.36 plus 1.08. So T follows a Poisson distribution, and its lambda is, that gives us 2.44. Now we're looking for the probability that T must be less than 3. Okay, so that's the probability that T is 2, 1, or 0. So that's going to be e to the negative lambda, which is 2.44, times T is 2, so 2.44 squared over 2 factorial. T is 1 will be 2.44, and 0 is just 1. Let's punch this into the calculator. That's e to the negative 2.44 times 2.44 squared over 2 factorial plus 2.44 plus 1, and this gives us a final answer of 0.559 to 3 significant figures. Part C. The probability that there will be no cars passing through the toll booth Y during a t-minute period is greater than 0.70. Find the largest possible value of t. Okay, so let's start by defining our random variable. I'll call it R. Okay, this will be number of cars passing through toll booth Y. Number of cars passing through Y, toll booth Y, toll booth Y per t minutes. So R is going to follow a Poisson distribution. But how would we find lambda? We know that for a 10-minute period, if we're going through booth Y, for a 10-minute period, our lambda is 2.7. What about if it's t minutes? So for t minutes, it's going to be simply t over 10 times 2.7. Notice that's exactly what we're doing earlier here. We wanted a 4-minute period here, so it was 4 over 10 times 2.7. Here we wanted a 4-minute period, and if we even go up here, we wanted a 16-minute period. So the same applies. Now it's just we're not dealing with an actual number, but we're dealing with t. So this would simplify to, this is 2.7 over 10. So we get 0.27t. This is our lambda. Okay, so R follows a Poisson distribution with lambda 0.27t. And we are told that the probability that there are no cars, so if there are no cars, it means R is 0, right? The number of cars passing is 0. During a t-minute period is greater, so greater than 0.70, 0.70. And the probability that R is 0, that's e to the negative lambda. Our lambda is 0.27t, and this must be greater than 0.70. So now we need to solve for t, so we can apply the natural logarithm on both sides. This is greater than ln 0.7. So the e and the ln cancel out, and you've got negative 0.27t is greater than ln 0.7. And now we need to divide both sides by negative 0.27 so that t is, remember, if you divide by a negative sign, your inequality changes direction. So this is ln 0.7 divided by negative 0.27. So that gives us t must be less than, let's punch that into the calculator, ln 0.7 over negative 0.27. This gives us 1.321 and so on. They say they want the largest possible value of t. Okay, so t represents the number of minutes. So the largest number of minutes we could have here is going to be the largest integer that's less than 1.321, which is just simply 1. So a 1 minute period. So our final answer is that t is 1. Number 2, the delivery times t minutes for a random sample of 60 parcels delivered by a courier service were recorded. The results were summarized by the summation of t is 2750 and the summation of t squared is 130,000. Part A. Calculate unbiased estimates of the population mean and variance of t. Alright, so let's start with the unbiased mean. So that's t bar. T bar is going to be the summation of t divided by n. So t bar is going to be, our summation is 2750, and n, our sample size, is 60. So that means t bar is equal to, that's 2750 over 60, which is 275 over 6 as an exact value, or we can give it correct to 3 significant figures as 45.8. Alright, so this is the unbiased estimate for mean. Now we also need to find the unbiased estimate for variance. So that's denoted by s squared, and the formula we use is 1 over n minus 1 times the summation of t squared minus the summation of t squared over n. So let's just substitute into our formula. So 1 over our n is 60, so n minus 1 is 59. Then the summation of t squared, that's 130,000, minus the summation of t, which is 2750, and this is squared, and this is over n. Our n is the sample size 60. So let's punch this into the calculator. So that is 1 over 59 multiplied by 130,000 minus 2,750 squared over 60. And this gives us, this is 11,875 over 177. Okay, so if we're to give this to 3 significant figures, this is 67.1. And this would be our unbiased estimate of population variance. Now we're told that you should now assume that your estimates from part A are the true values of the population mean and variance of t. So what that means is that the expectation of t is going to be our unbiased estimate for mean. I'll use the exact value there, 275 over 6. And then our population variance for t, so var of t, is now going to be our unbiased estimate. So 11,875 over 177. And then part B goes on to say the delivery times for another random sample of 60 parcels were noted and the sample mean T bar was found. Find the value of A such that the probability that T bar is greater than A is 0.623. Alright, so T bar, that's the sample mean for 60 parcels. This is going to follow a normal distribution, and its mean is going to be the population mean, 275 over 6. And remember, variance for a sample mean is sigma squared over n. So in this case, our sigma squared is this population variance. So 11,875 divided by 177, and it has to be divided by n, our sample size 60. So divide by 60. So let me just rewrite this. So our mean is still 275 over 6, and I want us to simplify our variance. So that is 11,875 over 177 over 60, which gives us, this is 2375 over 2124. All right, now let's look at the problem. We are given that the probability that t bar is greater than a is equal to 0.623. So the probability that t bar is greater than a is equal to 0.623. So if we standardize, we'd have that the probability that z is greater than, that will be a minus our mean, which is the 275 over 6, 275 over 6, divided by the square root of our variance. So square root of 2375 over 2124, and this should be equal to 0.623 still. All right, so I'm just going to replace this whole thing with a small letter z. All right, and this is 0.623. So if we can find this z value, then we should be able to use that to help us find a. So if we draw a bell curve, what this tells us is that the area to the right, because greater than, to the right of z must be 0.623. So it means z is probably somewhere here, and the area to its right is 0.623. And so from this diagram, because z is to the left of 0, we know that z is going to be negative. And then we can read our z tables in reverse and find the z value that corresponds to this probability, 0.623. So that z value would be 0.313. So remember here we replaced this whole expression with z. So what we're saying is that this z is the same as a minus 275 over 6 all over the square root of 2375 over 2124. So we can say that since we know what z is, we can say that negative 0.313 is equal to a minus 275 over 6 divided by, this should be a 6, divided by the square root of 2375 over 2124. Now we need to solve for a, so let's start by getting rid of our denominator, multiply both sides by this square root. So we'd end up with a minus 275 over 6 is equal to negative 0.313 multiplied by the square root of 2375 over 2124, which gives us negative 0.3309778, and so on. So a must be, add 275 over 6 to both sides, and so we end up with a is equal to 45.5, correct to 3 significant figures, and that is our final answer. Now on to question number 3. The time spent by customers in a grocery store checkout line has a normal distribution with standard deviation of 3.2 minutes. For a random sample of 30 customers, the mean time spent in the line was found to be 12.4 minutes. Part A. Calculate a 90% confidence interval for the population mean time spent in the checkout line. So the formula we're going to use, since we're looking at a population mean and we're using a normal distribution, is x bar plus or minus z times sigma over root n. So x bar we were given to be 12.4, that's our sample mean. Then z we need to find, sigma is 3.2 and n is 30. So since we are looking at a 90% confidence interval, it means that 90% of our area is going to be in the middle. So this area here is the 90%. And then, so on either side, we're going to have 5%, so 0.05 and 0.05. So to find our z value, which would be at this point here, we're going to say z is arc-phi of the area to the left of z, which is a total of 95% or 0.95. So we need the z value that corresponds to a probability of 0.95. And that z value is 1.645. Okay. So now we have everything we need to be able to calculate our 90% confidence interval. So it's going to be our sample mean, which we said is 12.4, plus or minus z, which is 1.645, times our sigma, 3.2, divided by the square root of n is 30. Okay. And now we can just punch this into the calculator. We'll start with the lower bound of our confidence interval. So 12.4 minus 1.645 times our 3.2 over the square root of 30. And this gives us, that is 11.4 to 3 significant figures. And so the upper bound is going to be 12.4 plus 1.645 times 3.2 over root 30. And this gives us 13.4, correct to 3 significant figures. So this is our 90% confidence interval. Now we're told that a student was asked for the meaning of this confidence interval. The student replied as follows. The times for 90% of the customers are likely to be within the confidence interval. Part B. Explain briefly whether the statement is true or not. So it is not true. What a confidence interval tells us is that in this case, since it's 90%, we are 90% confident that the population mean time lies within this interval. Okay. So the key here is that this confidence interval is focused on the mean time. This is how confident we are that our population mean is going to be between these two values. So our student here is talking about the times of 90% of the customers. So it does not, so confidence interval is not about individual times, it's focused on the mean time. So we can say this is not true because confidence intervals are about mean time, are about population mean time, to be more precise. Population mean time, not individual values, because or the student is talking about individual values. Population mean time, not individual values. Not individual values. Okay. And now we're given that two independent 90% confidence intervals are found. Given that at least one of these intervals contains the population mean, find the probability that both these intervals contain the population mean. Okay, so this is conditional probability, right? Because of this word given. So the formula for conditional probability is the probability of B given A is equal to the probability of the intersection of A and B divided by the probability of A. So we need to define what A is, what B is, so that we can figure out what our probability is. So A is the given event, B given A. The given event is that at least one of the intervals, so at least one, has true population mean, as true population mean. And then B would be the other event, which is both intervals contain. So both intervals have true population mean. So what would A intersection be? It would be at least one as true population mean and both intervals of true population mean. So that would just mean both intervals have true population mean, because the only way in which both intervals have the true population mean and at least one of them has the true population mean is only if both of them have the true population mean. So this is just the same as event B. Both intervals have true pop mean. Okay. True population mean. So we need to find, for starters, according to our formula, we need the intersection. So the intersection is the probability that both our intervals have the population mean. So since these are 90% confidence intervals, the probability of any of our confidence intervals having the true population mean is our confidence level, or 90%. And since we've got two of them, it's times 0.90 if both of them must have the true population mean. So let's simplify this. A intersection B is equal to, this is 0.9 times 0.9, which is 0.81. And then we also need to find the probability of event A. So at least one of them has the true population mean. So we can find A in one of two ways. So the first way to do it is to think of it this way. Since we want at least one of them to have the true population mean, it means either the first interval has the true population mean and the second does not, or the first does not and the second does. Or the final scenario being both of them have, right? Or both have, the probability that both have. Okay, so this is one way of thinking about it, and then we can just substitute in. So the probability of the first interval having the true population mean, since it's 90% confidence interval, is 0.9 times the second not having. So if we are 90% confident that it has the true population mean, it means that there's a 10% chance that it does not. So it would be times 0.10. Or remember, or just means we're adding, or it could be swapped. So the first does not, which would be 0.10, and the second does, so 0.90, or both of them have, which is just 0.90 times 0.90. All right, and then let's just punch this into the calculator. So that's going to be 0.90 times 0.10 plus 0.10 times 0.90 plus 0.90 times 0.90, which gives us 0.99. Okay, now another way to think of finding A, it's going to do it on the side. Another way for finding A is to think of it this way. We want at least one of our intervals to have the true population mean. So this is just the same as 1 minus the probability of none of them having the true mean, right? None of them having the true mean. Because if we remove the probability that none of them have the true mean, the ones that remain are going to be either the first one has it, or the second one has it, or both of them have it. So this is a quicker way of doing it, if you understand it. So it's going to be 1 minus, so the probability of the first interval not having, since it's 90% confidence interval, not having would be 10%. So it's 0.10, and there's two of them, so 0.10. And if we punch this into the calculator, this is 1 minus 0.1 times 0.1, and this gives us 0.99, which is exactly what we got with the other method. Okay, so now that we have our probabilities, we can just substitute into the formula for conditional probability. So the intersection is 0.81, and then A is 0.99. And this gives us that the probability of B given A is therefore equal to 0.81 divided by 0.99, which is 9/11. Okay. Number 4. A random variable x has the probability density function if defined by f of x is 5/16 times a over x squared minus 15 over x cubed when x is between 3 and 5 inclusive. Otherwise, f of x is equal to 0, where a is a constant. Part A, show that a is equal to 28. Okay, so to find A, the idea we want to use is that the total area under the PDF must be equal to 1. So if we integrate from our lower bound 3 to our upper bound 5, we should get a total area of 1. So I'm going to take the 5/16 outside so that we're integrating A over x squared minus 15 over x cubed with respect to x, and this must be equal to 1. So let's bring up our x squared and our x cubed so that we can integrate this. So that's 3 to the 5, and now we've got ax to the negative 2 minus 15x to the negative 3. This is all with respect to x, and this must be 1. If we integrate, we've got 5/16. Then ax, add 1 to negative 2, you get negative 1. Divide by this new power, so divide by negative 1. Then we've got minus 15x. Add 1 to negative 3, you get negative 2. Divide by this new power, so divide by negative 2. And this is from 3 to 5, and this must be 1. Alright, so if we simplify this, what we have is 5/16. And this is now, because of the negative 1, it's negative a, and then I'm going to take the x to the negative 1 down to the denominator, so it's just x. And then here our negative signs cancel out, so we've got positive 15/2. If we take x to the negative 2 down to the denominator, it's x squared. And this is from 3 to 5, and this should be equal to 1. So now we can go ahead and substitute in our limits. So we'll start with the upper limit 5. It's going to be negative a over 5 plus 15/2 times 5 squared. 15/2 times 5 squared minus our lower limit. So that's negative a over 3. Negative a over 3 plus 15/2 times 3 squared. 15/2 times 3 squared. And this should all be equal to 1. So let's simplify. We've got 5/16 times, here we've got negative a over 5. Then we've got 15/2 times 5 squared. 15/2 times 5 squared simplifies to 3/10. Minus, we've got minus a over 3. And then 15/2 times 3 squared, which is 5/6. And this should all be equal to 1. Let's continue to simplify. So for the upper bound, it's just negative a over 5 plus 3/10. Then for the lower bound, we want to multiply through by our negative sign there. So it's negative times negative a over 3, which is positive a over 3. Then negative 1 times 5/6, so negative 5/6. This is 1, so we've got 5/16. And we have like terms, so negative a over 5 plus a over 3, so that's negative 1/5 plus 1/3, which is 2/15a. And then we've got 3/10 minus 5/6, so 3/10 minus 5/6, this gives us negative 8/15, and this should all be equal to 1. Let's multiply through by 5/16. So 5/16 times 2/15. 5/16 times 2/15, that gives us 1/24a. And then 5/16 times negative 8/15. So 5/16 times negative 8/15, that's minus 1/6. And this should be equal to 1. And now we're just solving for a. So we get that 1 over 24a is equal to 1 plus 1 over 6. So 1 over 24a is equal to 7 over 6. Multiply both sides by 24. And we get that a is equal to 7 times 4. So a is in fact 28. Alright, that's exactly what they wanted. Part B says, show that the expectation of x is 35 over 4 ln 5/3 minus 5 over 8. Alright, so the formula for expectation is the expectation of x is equal to the integral of all x of x f of x with respect to x. So this just means integrate from your lower bound to your upper bound and then multiply x times your f of x with respect to x. So we are integrating from our lower bound is 3 all the way up to 5, and this is going to be x multiplied by, what is our f of x? So our f of x is now 5 over 16 times our a, we said is 28, so 28 over x squared minus 15 over x cubed. Okay, so I'll just take the 5 over 16 outside the integral sign, and so what remains here is going to be the 28 over x squared minus 15 over x cubed minus 15 over x cubed, and this is all with respect to x. So 5 over 16, the integral from 3 to 5. Here x and x squared. Here the x would cancel out the x squared, so that is just 28 over x. And then for the second term, it would be minus 15 over x squared, and this is with respect to x. So if we take it to the side here, what we're going to have is 5 over 16, the integral from 3 to 5, and then we've got 28 over x. Then I want to bring the x squared up so that we can integrate it. So that's 15x to the negative 2. And this is with respect to x. So that's going to be 5 over 16 and 28 over x. If you integrate this, it's 28 ln x. Then we've got minus 15x to the negative 2. So add 1 to negative 2, it becomes negative 1, divide by the negative 1. And this is from 3 to 5. So we've got 5 over 16. All right, let's substitute in our, okay, so we can rewrite this as 28 ln x. And then here the negative 1 and the negative 1 cancel out. So it's just going to be positive 15 over. We can take the x to the negative 1 down to the denominator so that it's over x. And our limits are from 3 to 5. Now we can substitute in our limits. So that's 5 over 16. Start with the upper limit. So that's going to be 28 ln 5 plus 15 over 5. Then our lower limit. So that's 28 ln 3 plus 15 over 3. Okay. So we've got 5 over 16. And then we've got 28 ln 5. 15 over 5 is just 3. Then here we've got minus 28 ln 3. And then we've got 15 over 3 is 5. So it's minus 15 over 3, so minus 5. And so this is 5 over 16 times 28 ln 5 minus 28 ln 3. And we've got 3 minus 5, which is minus 2. So using laws of logarithms, we know that ln A minus ln B is equal to ln A over B. So we want to use that same law here. So it's going to be 5 over 16 times 28 ln 5 over 3. 5 over 3, and we've got minus 2. And now let's just multiply through by 5 over 16. So we've got 5 over 16 multiplied by 28, which is 35 over 4. And that's ln 5 over 3. Then 5 over 16 multiplied by negative 2. So that's going to be negative 5 over 8. and this is our expectation, and I believe this is the expression they wanted. Let's check. 35 over 4 ln 5/3 minus 5 over 8. Correct. Perfect. Number 5. The weights in kilograms of a certain breed of puppies are normally distributed with mean mu and standard deviation 2.3. An article in a pet magazine states that the value of mu is 4.5. A veterinarian wishes to test whether this value is correct. He records the weights x kgs of a random sample of 50 puppies of this breed and finds that the summation of x is 259.8. He plans to carry out a test at the 2% significance level to determine whether the true value of mu is different from 4.5. Part A. State for the reason whether he should use a one-tailed test or a two-tailed test. So that answer is given by this word. Because we're not testing for a definite decrease or a definite increase, we are just looking for a difference or a change. We don't care which side it is. It means we're going to use a two-tailed test. So two-tailed test, because we are testing for a change or a difference, because we're testing for a difference. Testing for a difference. Okay. And now part B says carry out the test. Alright, so we've got the weights in kilograms of a certain breed of puppies, so I'll denote that with W. And we know that these are normally distributed, so it follows a normal distribution with mean mu, so mu, and standard deviation 2.3 squared. 2.3 squared, or standard deviation is 2.3, so variance is 2.3 squared. We need to start off by defining our now and alternative hypothesis. So H naught, the now hypothesis, would be that our mean is still the same. So our mean is still 4.5, right? And then our alternative hypothesis would be that our mean is different. So our mean is different just means it's no longer equal to 4.5. We don't know if it's less than 4.5 or if it's greater than 4.5. And we don't really care whether it's less than or greater than. We just want to know if it's different. Okay. So assuming H naught is true, we can define our sample mean, the distribution of our sample mean, W bar, saying that W bar follows a normal distribution and its mean is going to be the mean from H naught, because we're assuming H naught is true. And then the variance, remember, is going to be sigma squared over n. So 2.3 squared, which is our sigma squared, over n, which is the size of our sample. Our sample is of size 50. So 2.3 squared over 50. Okay. And now we need to come up with a rejection rule for our test. So I'm just going to draw a bell curve so that we can visualize what on earth is going on. So this is a test at what significance level? It's at the 2% significance level. So it means we want 1% on either side. So if you've got a two-tailed test, you split the significance level into two so that you've got half of the significance level on this side and the other half on this side. Okay. This is specifically for a two-tailed test. And then in the middle is going to be 0.984. To be consistent, since I'm using percent, it's going to be 98%. All right. So our Z value for our critical region are going to be, Z would be arc-phi of, if this is Z, then the area to the left of Z is 99%. So we want the Z value at a probability of 0.99. So that Z value is 2.326. Okay, so here we've got 2.326, and this would be negative 2.326. So we are going to reject H naught if our calculated Z value, is in the critical region. So either it's less than negative 2.326 or it is greater than 2.326, because that's when it will be in our critical region. If you're comfortable with modulus, you can write this expression as simply the modulus of z is greater than 2.326. If you're not, then don't worry about it. Ignore this modulus thing. All right, so now we need to calculate what z actually is. So z, remember to calculate z is going to be x bar minus mu over sigma over root n. So z is going to be, x bar is the test statistic. So when whoever is investigating carries out their sample, the investigation on the sample, the mean that they get from that sample, we call that our test statistic. So our vet here is testing whether this value is correct, and he gets a random sample of 50 and finds that the summation of x is 259.8. So the mean from that sample x bar is the summation of x over n, right? So that's going to be the summation of x is 259.8 divided by n being the sample size 50. So it means our test statistic is going to be 259.8 divided by 50, and this is 5.196. So we'll use that to help us check whether the vet's claim that the mu must be different is true. So z is going to be 5.196 minus our mu. We get our mu from this distribution that we defined here. So that's going to be 4.5 divided by sigma over root n. So 2.3 over root 50. 2.3 over root 50. So our z calculated is 5.196 minus 4.5, and this is being divided by 2.3 over root 50, and this gives us a z of 2.140 to 3 decimal places. Okay, so let's compare this to our critical values here. 2.140 we can tell would probably be somewhere here. So it is less than the 2.326. And so we're not in the rejection region, so we do not reject H naught. Do not reject H naught. And we conclude that there is insufficient evidence. There is insufficient evidence at the 2% significance level to suggest that the mean is different, to suggest that mu is different. Mu is different. Okay. So we can't really support the vet's suspicion that the true value of mu is different. All right, so this is our final answer. That's our test. Number 6, the heights in centimeters of two species of sunflowers, species X and species Y, follow independent distributions, normal with mean 90 and variance 10.5 squared, and normal with mean 60.0 and variance 8.2 squared, respectively. Part A. Find the probability that a randomly chosen species X sunflower is more than twice the height of a randomly chosen species Y sunflower. So we're looking at the probability that a species X sunflower is more, so greater than, twice, so times 2, the height of a species Y, 2 times Y. Okay. And so to find this probability, let's put both our random variables on one side. So x, I'll move the 2y to the left, so it's x minus 2y. This should be greater than 0. And then just so that we don't have to keep writing x minus 2y, I'll define it as d. D is x minus 2y. So to be able to find this probability, we need to find the mean of d and its variance as well. So the mean of d is going to be the expectation of x minus 2 times the expectation of y. The expectation of x minus 2 times the expectation of y. So the expectation of d is equal to, what's our expectation of x? That's the 90.0, minus 2 times our expectation of y, that's the 60.0. So the expectation of d is equal to, let's punch this into the calculator, that's 90.0 minus 2 times 60.0, and this gives us negative 30. And now for the variance of d is going to be the variance of x plus, now this is where it's crucial to differentiate between a sum and a multiple. So because they said more than twice, it means times 2. And anytime you're multiplying, we call this a multiple. Okay? And the alternative to a multiple is a sum. So people tend to confuse the two, whether it's a sum or a multiple. Calculation for the expectation is the same for both mean and sum. But if you've got a multiple, which is usually of the form nx, its variance, the variance of nx is going to be n squared times the variance of x. Whereas if this was a sum, it would be of the form x1 plus x2. So in general, it's anything of the form x1 plus x2 all the way up to xn. So in general, if you want the variance of this, it's going to be, it's not n squared by x, it's just n by x. So that's the catch. If you can't differentiate between a multiple and a sum, then you're going to struggle with getting the correct variance. Once you know that it's a multiple, you know that your variance is going to be of the form n squared by x. So in our case, because we identified that it is a multiple, we're going to say plus negative 2 squared, or just 2 squared, times the variance of y. So var of d is going to be, what's our var of x? 10.5 squared plus 2 squared, which is 4, times the variance of y, which is 8.2 squared. 8.2 squared. So the variance of d is, let's punch that into the calculator, that's 10.5 squared plus 4 times 8.2 squared, and this gives us, that's 379.21. Now, because d is coming from x minus 2y, x and y are both normally distributed, it means d is also going to follow a normal distribution, with its mean being negative 30 and its variance being 379.21. And we said we wanted to find the probability that x minus 2y is greater than 0. Remember, x minus 2y is just d, so we want the probability that d is greater than 0. So that's going to be the probability that, if we standardize, z is greater than 0 minus 30, so plus 30, over the square root of 379.21. And so this is the probability that z is greater than, let's punch this into the calculator, that's 30 over the square root of 379.21, and this gives us 1.541 to 3 decimal places. And to find this probability, that's 1 minus phi of 1.541, and we need to read off the value of phi of 1.541 from our tables. So that's 0.9383, and if we subtract 1 minus 0.9383, we get 0.0617, and that's our final answer. Now we're told that the sunflowers are planted in fields The fields are identical in appearance. 70% of the fields contain exactly 15 randomly chosen species X sunflowers. 30% of the fields contain exactly 25 randomly chosen species Y sunflowers. Part B. Find the probability that a randomly chosen field has sunflowers with a total height of more than 1,400 centimeters. Okay, so here we've got two types of fields, right? We've got the first type of field, and this type of field is going to contain exactly 15 randomly chosen species X sunflowers. Now, because these are 15 randomly chosen sunflowers species X, these are going to be independent observations of the same random variables, and we call that a sum. So what we're looking at is x1 plus x2 all the way up until x15. All right. And so this here would give us the total height of the first type of field, in which we only have 15 of species X sunflowers. Okay. And so that we don't have to keep rewriting this over and over again, I'm going to code this, we can code this if, right, for first field. And so for this first type of field, we need to find the probability that its total height is more than 1400. So the probability that if is greater than 1400. Did I say 1400? I'm watching too much American content. Anyways, all right. So we've got a second type of field, right? Second type of field. And in this field, we've got exactly 25 randomly chosen species of sunflower. Why? Now, because again, these are independent observations, 25 independent observations of the species Y sunflowers. This is a sum. So it's Y1 plus Y2 all the way up to Y25. Okay, and I'll denote this as S. And again, this is the total height for this field that only contains our species Y sunflowers, so total height. And we need to find the probability that the total height of this type of field is 1,400, not 1,400. So these are the two scenarios that we have. So let's evaluate their probabilities separately. And then at the very end, we'll factor in that we only have 30% of fields with the species Y, and then the other 70% are species X. So we'll start with this first one, the probability that our first field has a total height that's greater than 1,400. So to evaluate that probability, we first need to find our mean. So our mean, this is a sum of 15 independent observations of X. So it's 15 times the expectation of X. So the expectation of F is 15 times what's the expectation of X is in part A. That's going to be our 90.0, right? So 15 times 90.0. And this gives us that our expectation is what? 15 times 90. 1,350. And we also need our variance. So the variance of F is, as I mentioned in part A, when we're talking about the difference between a sum and a multiple. So since we have identified that this is a sum, because these are independent observations of the same random variable, instead of saying 15 squared times the variance of X, we're going to say just 15 times the variance of X. That's how you calculate the variance of a sum, right? So the variance of F is 15 times the variance of X. Variance of X is 10.5 squared, right? Yeah. Okay, so 15 times 10.5 squared. And so the variance of F is equal to, let's punch this into the calculator, 15 times 10.5 squared. That gives us 1653.75. Okay, so now that we have both mean and variance, notice that F is essentially coming from the random variable x, which is normally distributed. So it means that f would also be normally distributed, and its mean is 1350. Its variance is 1653.75. And we want the probability that f is greater than 1400. So the probability that f is greater than 1400, that's going to be the probability that z is greater than 1400 minus 1350 over, that's our square root of 1653.75. So the probability that z is greater than, let's punch this into the calculator, 1400 minus 1350 over the square root of 1653.75, and this gives us 1.230 to 3 decimal places. So this is 1 minus phi of 1.230. So let's read off the value of phi of 1.230 from our normal distribution tables. So that's 0.8907. So 1 minus 0.8907, that gives us 0.1093. So this 0.1093 is the probability that the first type of field, the field that only contains species X, that its total height is greater than 1400. The probability of that happening is 0.1093. We'll factor in the percentages at the very end. I just want us to go through the same calculation for the second field as well, because we need to check, or we need to find the probability that the total height of the second type of field is greater than 1400. So for starters, we need to find the expectation of S. So that's going to be, we've got 25 of these species Y flowers. So 25 times the expectation of Y. So the expectation of S is 25 times, what's the expectation of Y? Expectation of Y is our 60.0. So times 60.0, and this is equal to, so 25 times 60, that gives us 1500. And then we also need the variance of S. So again, because it's a sum, it's just 25 times the variance of Y. And so the var of S is equal to 25 times the variance of Y, which is 8.2 squared. So times 8.2 squared, and this is equal to, so 25 times 8.2 squared, that gives us 1681. So now that we have the expectation and the variance for S, we can define its normal distribution, having a mean of 1500 and a variance of 1681. And we are looking for the probability that S, or the total height of our second type of field, is greater than 1400. So the probability that S is greater than 1400. So that's the probability that if we standardize 1400 minus 1500 divided by the square root of 1681, so the probability that Z is greater than, let's punch that into the calculator, 1400 minus 1500 divided by the square root of 1681, and this gives us negative 2.439. So this is just phi of 2.439. So let's read off the value of phi of 2.39 from our normal distribution tables. So that's 0.9906. So this is the probability that the total height in the second type of field is greater than 1400. But now we also have to factor out that we only have 70% of the first type of field, and we've got 30% of the second type of field. So we need to multiply each of the probability of picking one of the two fields by their respective percentages, right? So we said for the first type of field, the probability that its total height is greater than 1400 is 0.1093. And then for the second type of field, the probability that its total height is greater than 1400 is 0.9906. 0.9906. But what is the probability that we're able to select each of these fields? So there's a 70% chance that we select the first type of field, and then there is a 30% chance that we select the second type of field. So we have to factor that in as well. So that becomes 0.1093 multiplied by 0.7 plus 0.9906 multiplied by 0.30, which gives us a final answer of 0.374. Number 7, a gym owner models the number of members who use the gym sauna on any given day by the distribution binomial, where n is 13 and the probability of success is p. In the past, the value of p was 0.7. The owner introduces a new relaxation package and wants to test whether the value of p has increased. On a randomly chosen day, he notes that the number of members who use the sauna is 25. Part A. Use the binomial distribution to carry out the test at the 5% significance level. So let's start off by defining our random variable, and we'll call it G. We're looking at the number of gym members who use the sauna. Number of gym members who use the sauna on any given day. Number of members who use sauna on any given day. Okay. And we are told that G is binomially distributed with n is 30 and p is p. Let's state our null and alternative hypothesis. So in the past, the value of p was 0.7. That's our null hypothesis. And we want to test whether this value of p has increased. So we want to test if p is greater than 0.7. Now, assuming h0 is true, we can redefine our G. Assuming h0 is true, it allows us to use p as 0.7. So it would mean that G follows a binomial distribution, n is 30 and p is 0.7. And we want to carry out this test at the 5% significance level. So we would reject h0 if we found that the probability that, in this case, G is, we take the sign of our alternative hypothesis and we add an or equal to sign. If the probability that G is greater than or equal to whatever value we're testing, if this is less than our significance level, so if it's less than 5%, we are going to reject H0. Okay. So our gym owner goes out on a randomly chosen day and he knows that the number of members who are using the sauna is 25. So we need to test this value of 25 and check to see if it gives us enough evidence to suggest that, the number of people who use the sauna has increased. So we need to calculate the probability that G is greater than or equal to 25. So that's going to be the probability that that's 25, 26, 27, this is long, 28, 29, and 30. Okay, so let's do that on the side. So probability that G is greater than or equal to 25, we're using this distribution here. So it's going to be 30 choose 25 times 0.7 to the 25 times 0.3 to the 5 plus, then we go on to 26. So 30 choose 26 times 0.7 to the 26 times 0.3 to the 4 plus 30 choose 27 times 0.7 to the 27 times 0.3 to the 3 plus 30 choose 28 times 0.7 to the 28 times 0.3 squared plus 30 choose 29 times 0.7 to the 29 times 0.3, and then finally 0.7 to the 30. This is when G is 30. Okay, so let's punch this into our calculator, this whole thing. So that is 30 choose 25 times 0.7 to the power 25 times 0.3 to the power 5 plus 30 choose 26 times 0.7 to the power 26 times 0.3 to the 4 plus 30 choose 27 times 0.7 to the 27 times 0.3 cubed plus 30 choose 28 times 0.7 to the 28 times 0.3 squared plus 30 choose 29 times 0.7 to the 29 times 0.3 plus 0.7 to the 30. And this gives us 0.07, that's 66. And let's compare this to our rejection rule here. Our probability is 0.0766. Is it greater or less than our significance level? It is greater than 0.05. So we're not in the rejection region. We are not going to reject H0. So do not reject H0. Do not reject H0. And we can conclude that there is insufficient evidence. There is insufficient evidence. At what level? At the 5% significance level to suggest that the number of people who use the SONA has increased, to suggest that P has increased. You can write the long one that the number of people who use the SONA has increased. That's probably the better answer, but both will be accepted. All right. And then part B says, given that there are 35 members at the gym, comment on the suitability of the owner's model. Okay, so we can make an argument for both cases. We could argue that the owner's model is suitable in the sense that even though in our model we are investigating with only 30 members, logically speaking, right, chances are on any given day you're not going to have a total of all the 35 members, right, attending on that day. Not everyone is going to come to the gym on that specific day. So you might find that of all the 35 members, you might only have maybe 20 something people who actually come to the gym on that particular day. So a model of 30 would still work. Okay. But I could also just as well make a counter argument that if you know that you've got 35 members at your gym, then use a model of 35 members to calculate, to evaluate your situation. Don't use a model of 30. So as long as you can argue it out, then your answer would be correct. So in this case, I will go with it is suitable. It is suitable because not all 35 members will be at the gym on any given day. Will be at the gym at any given day. At any given day. Okay. And this would be our final answer. And that is the paper as well. Oh my word. This was that linear combinations question wasn't fun. Okay, anyways, all the best for your exams. I wish you all the luck you could have. Remember to relax and breathe in the exam. And yeah, good luck. If you enjoyed this video, like the video, subscribe, share the video with others, and all the best in your exam. You got this, trust me. Stop putting too much pressure on yourself. You're going to ace this exam. Well, if you prepared, of course. If you didn't, well, good luck.